Of everything we have discussed. Remember, started from the birth of the beam within the X-ray tube, the anatomy of the X-ray tube, the when Photon meets the patient, and controlling the journey, prevention, and decreasing or minimizing scatter, catching the exit of the beam. Remember this, and then making sure diagnosis that factors affecting the image quality. When image lies, that's lecture 6, where we discuss regarding the artifact mammography. How can we use a smaller or lower dose, such as low kbp, to measure a specific part of the body, fluoroscopy, and angiography DSA. So this is going to be just a recap so they can just remember everything at once. At the X-ray tube that's starting the path of the X-ray, we have our X-ray which is coming out as a result of electron going from the cathode to the anode direction, and then the X-ray coming from the window. We have our X-ray tube, the KBP, which determines the acceleration and the quality of the X-ray, the intensity of the X-ray, where the A mostly determine the quantity of the X-ray and noise. And then we have discussed regarding the filtration, especially low energy that will be filtrated to target important target to the waveform, that most of the electron energy becomes heat as they come to the target, as they hit the target area. So 99% will become heat, only 1% will becomes X-ray. Out of that 1%, we've said of that only 20% will be contributed from the characteristic radiation. The 80% is going to come from the bremsstrahlung, which means breaking radiation, which is continuous from the low to high energy. And then the next part of the lecture, we discussed regarding when the X-ray comes out of the tube and then it emits matter. So what we have in the photon emit matter, and this we've discussed. We have got X-ray coming, the incident beam to the patient. So many things happens, mostly three of them. So that could be photoelectric effect or absorption, where the X-ray will be absorbed by the tissue, depending mostly on the AD, atomic number, density, and the energy as well. As the energy increases, the Compton mostly overtake or predominate in high energy, whereas photoelectric become more beta in low energy. And as a photoelectric, we have said we've got transformation, the instant beam which passes through the patient that will take the main information from the patient without undergoing anything, without undergoing the Compton, no photoelectric effect, no photo disintegration, nothing. This is the main remnant beam that will contribute to the color, the image, that will form image. Whereas if scatter, the high energy, high angle will lead to a forward scatter that may lead to degradation of the image quality, and the scatter mainly comes from the Compton scatter. Also, linear attenuation coefficient mu is inversely related to the half value layer, and linear attenuation coefficient equals atomic number density over energy. So when atomic number and density increases, the linear attenuation coefficient will go up, and then the vice versa is going to be have value layer. The value layer equals energy over linear over AD, atomic and density. So the higher the energy, the higher the value layer, and vice versa. Meaning the higher the density and the atomic number, the less the value layer. So now, what about the part what lecture 3? In lecture 3, we mentioned regarding the like controlling the journey of the beam. So we got our remnant beam going out, coming out of the patient, and the beam, which is the remnant, does not undergoes anything, neither uh neither Compton, no photoelectric or photointegration, nothing, no absorption, no scattering. So directly transmitted. This is a remnant beam that is going to contribute to the image formation. So that image must we're doing something in the controlling journey to get to get only the remnant beam as far as much as we can and remove most of the scatter so that we can get better image and better quality image. So image, we started with the filtration before the main photon, the X-ray coming out of the tube before reaching the patient. So filtration, collimation. Then we went through compression at the patient level. Then we used grid, air gap levels, assay, geometric such as playing with the object to image or detect a distance while maintaining magnification using smaller focal spot to help get decreasing or minimizing blurring and and sharpness. So these are all part of lecture 30. And also remember, grid, we have mentioned that grid will increase dose to the patient, whereas air gap also increase dose, but still air gap is the dose that would be increased, the air gap will be lesser. So in the lecture 4, we discussed regarding catching the X of the beam, like when the beam reached detector level. So at the detector level, what's happening? Well, two types of detector go CR, computerized, and digital one. For the CR, mostly the as a remnant X-ray comes, it's going to hit the plate, the phosphor at the beginning of the plate after the coating layer. So that phosphor mostly PSP, photostimulable phosphor, which is made from barium fluorohalide. That barium fluorohalide phosphoplate could be bromide, could be iodide. So that would start changes inside the structures and form a latent image. The latent image is going to get exposed to a red laser light that will read out to get our image, and then immediately the plate is going to be erased using white light. So when coming to the main digital detector, is divided into two types. We have indirect and direct. The main difference between indirect and direct is that for indirect, okay, the X-ray, normally X-ray coming will be converted into light first before getting converted into the charges. So we get scintillator, which mostly forms from cesium iodide and sometimes gadolinium oxysulfide, which is powder. So each one has its advantage. So for beta DQA, detective content efficiency, with for overall for the digital detector. Then that light is going to be converted by photodiode into a electric charges. That's mean photo means light, diode, that from light to electric charges. So the photodiode mostly in the indirect is made from amorphous silicon. Remember, we have amorphous selenium indirect. In indirect, the food diet is amorphous silicon. In the direct, is just the food diet is amorphous selenium, which will convert the remnant X-ray directly into electric charge. Then both of them are attached to TFC, the conversion formation of the image, and then image will be instantly displayed on the monitor. So now comes to lecture 5, making image of diagnostic. We discussed regarding the quality factors affecting image quality. Objects versus detector, displayed contrast, signal to noise ratio, contrast noise ratio, magnification, difference between magnification and digital zooming, resolution versus noise, dust reduction, diagnostic advocacy, increases MA, reduces content noise, but increases dose at some time. DQA, describe detector efficiency in preserving signals to noise ratio at the same level as same amount of photon. Lecture 6 mentioned regarding when image lights artifacts. What are distortion, artifact exposure, over and underexposure does creep, especially in digital system, whereby we cannot detect whether the image is overexposed. And then go come to lecture 7, mammography. The most important, the mammo is you understand the target filter combination. We have mentioned very important point that the main KH of the filter must be always higher than the KH of the target. That's why we cannot use Ramo. We cannot place rhodium as a target and molybdenum as filter, because the KH of radium is beta is higher, mostly between 20, 22 or 23, whereas the molybdenum between 17 up to 19 or 20. So molybdenum KH is less than rhodium, so we cannot place rhodium as target and while using molybdenum as a filter. So what we can use Momo for thin, small breast, medium breast, mostly Mora, but we cannot say Ramo, we cannot start place target as a rhodium them filter. But we can use Rara as like rhodium as a target and rhodium as a filter. We can use a tungsten as target and rhodium as filter for dense braids, a very dense braids. Sometimes we can use place silver as a filter, and while using tungsten as a target. So importantly, and most thing to remember regarding mammogram is that it uses low energy, low kbp, mostly between 25 to 35. For smaller breast and less thin breast, we prepare using 25 kbp. Whereas for larger braids and denser one, we prefer using higher ones, the upper limit around 35 kbp. Importantly, another thing very critical is MGD, main glandular dose, is more relevant to the glandular tissue of the skin. So mostly the MGD is more relevant than the skin dose for mammography when it comes to risk assessment. The next lecture was about what we call fluoroscopy and DSA. We have discussed that also into detail while we mentioned using either intensifier, image intensifier, II, or using flat panel detector. With the differences between both of them were discussed into detail. Fluoroscopy is mostly time alone, so it is looking, we're considering, or mostly we are looking after the temporal resolution, the time and the way we have taken. So that's why we are capturing like frame per second from 30, 15, 7.5 to 3. So the less the frame per second, the jitter is going to be the motion is going to be hectic and jittering, and the smoother motion will be with the more frame and the higher the dose. So the higher the motion, the better the motion, and the more the frame per second, the more the dose. Also, patient is the main source of scatter to the staff. That's why we are using under the couch source. And then we are measuring the cumulative dose in fluoroscopy. Remember also the DSA, we are just using photoelectric impact or implication on the X-ray image. So we capture an image, mask image with the out contrast, the pre-contrast image, then we inject contrast, iodine, then we subtract the mask image from the contrast. So it will remain only the contrast vessel. So this is important. But mostly now we are using MRA, MRI angiography, or using CT angiography and others. So these are all discussed in our 8 serial lectures regarding the X-ray. So if you have any problem, go back to specific lecture, watch it. Remember, we mentioned that we started with the tube spectrum, then the patient, remnant beam that are coming out, taking the information from the patient, and then detected or captured by the detector image formation, or you optimize the image regarding the quality factors affecting the part of safety. So the safety is going to be discussed under radio protection. So follow RadSound for more videos. And remember, we have our channel or our site where you can have your mock exam for physics at physics.radiologysound.com. So you have free access to many study material, many things which is going to help you to pass your exam. And into these 20 high-yield traps, they're all within our website, physics.radiologysound.com. Read through them, understand. Can you understand the traps? They say they are saying like collimation reduces radiated volume and scatter protection. True, false? True or false? True, because it reduces radiated volume. Then saying last email hold your hot last image in fluoroscopy uses no extra radiation, true or false? True. So if you have any problems, go back to the specific lecture or visit the website physics.radiologysound.com and check a specific book there called trap. So exam trap. In the exam trap, you'll see a lot of trap, more than 1,000 traps, and that will help you ace your exam as easy as possible and in the first seat. See you in the next section, which is going to be CTA.